Innatera basically develops what are called neuromorphic processors. I have the latest one, which is even smaller. It's a really tiny piece of silicon, and it's essentially in this small 2 millimeter by 3 millimeter chip, and that's the complete system, and it's a neuromorphic processor all in one.
You've got to see that. You've got to go and see the Innatera. You've got to see what they've done. It's mind-blowing.
Hey, it's Eamon from ipXchange, here to introduce another ipXperience interview, this time between Guy and Sumeet from Innatera. So this is a company that Guy's been wanting to get one of these from for a long time, and watch the interview, you'll see exactly why. They're an AI chip company, and there's some expertise there that a lot of other companies will wish they had. Enjoy.
Hello, IPXers. We're here again at the IPX studio. We're all about disruptive technology, you know that. And I'm joined today by Sumeet, who is the CEO of Innatera. Now, I've got a story about this company. I've been going to Embedded World for longer than I care to remember. And last Embedded World, I tend to go around the edges. I look for the really cool stuff around the edges because that's where the disruptive technology is. And I stumbled across Innatera. And rarely am I failed for words. But when I looked at their chip and what they had, I thought, wow, this is an amazing company. And I thought with Embedded World coming up in only 6 weeks' time, it'd be great to have a chat with Sumeet, understand where his company's come from, where he's come from, and how he's going to change the world. Because goodness me, he's got some big things that he says on his website. So let's hear about what you do, Sumeet. Tell me, first of all, tell me where the company comes from and where you come from. Tell me about you.
Sure thing. So, as you probably recognize from my name, I'm originally from India, and I moved to the Netherlands about 17 years ago, basically to study at the university in Delft. And as I hung around and I got exposed to the entire compute ecosystem. In 2018, we spun off close to 10 years of research that was being done at the Delft University of Technology in the areas of neuromorphic compute and energy efficient computing. We took all of those activities and we spun a company out of it. And our objective right at the beginning was basically to make sensors intelligent. That's how we started. We didn't really know too much about how exactly we were going to do it. But the only sort of inspiration and motivation that we had back then is we saw how efficient and effective the brain is at finding patterns inside sensor data and being able to process data coming out of sensors, even when it's in a really terrible condition. And that's basically what we wanted to capture and deploy towards processing of data that we have in these always on use cases, packed with sensors, producing complex data throughout the day. We wanted to make sense of all of that. So that's essentially why we started the company back in 2018. Innatera basically develops what are called neuromorphic processors. These are basically brain-inspired processors that mimic the same pattern recognition mechanisms that your brain uses, and it applies them towards making sense of patterns in sensor data in devices where power is a critical problem and where latencies really need to be extremely short. So we develop complete solutions that span silicon as well as software, essentially allowing customers to do this in an always-on fashion.
Right. Let's just backtrack you a little bit. Delft, I went there when I was a small child, and as far as I was concerned, that's where pottery came from. So how does a startup out of Delft University crack open? How does that journey for our engineers who are all going to be aspiring takers over the world, how does that start? Because, I know technology, particularly today, can start anywhere, but that's still quite a remarkable place to start. So what was the process that you went through to go from got a group of people around you, got this great idea, make sensors intelligent? You just described that. You've said that all the whole idea that you had, but there's a long way away from having an idea and starting a business. So just give us a little bit of background about how that came about, because that is very interesting.
Absolutely. The really great thing about doing this sort of building a company out here in Europe is that if you look at European universities, you don't very often hear too much about them, but they're filled with really great tech. And there's real substance to them. There's real depth, and they can really have a really solid impact on the world if we're able to commercialize this technology well. Um, when I was at Delft, when I went in to spin this company out from Delft, our initial idea was to make use of these sort of neuromorphic technologies to build sort of a medical device that would transform people's lives and make it easier for us to detect disease long before it became symptomatic. And it just
Okay.
so happens that that is a tremendously hard path to walk, not only because it's a medical device and that's fraught with a whole bunch of regulatory challenges which you have to overcome, rightfully so. But when you're trying to build a completely new piece of silicon under that sort of a device, it makes things all the more complicated. So when we started the company, it was with a completely different objective. And as we started executing, I think a lot of things fell away, and we focused on what the fundamental value proposition could be. How do you make sense of sensor data very efficiently? And that became effectively the mission of the company. We started to focus just on the silicon part of the story. And then we realized that there is such a broad range of applications that we could target. So we collaborated with the Delft University of Technology. We started doing our developments. We sought out industrial partners out here in Europe that engaged with us because they really saw that effectively what we were building was going to solve some of their most critical problems. And that problem back then, even back then, was the power problem inside of a tiny device like your smartwatch with a really tiny battery inside. How do you possibly process data coming out of a sensor every second of every day without having to recharge that device, every hour?
Yeah.
That was a critical problem that our customers were already seeing coming up over the horizon, and that's when they engaged with us. It allowed us to validate our market approach very early on in the game, and then we raised our first round of funding back in 2020, and we have been growing at an exponential pace ever since. We haven't looked back.
Right. So what's your team up to? I mean, I've actually, you have this little plastic box that you had in Embedded World. So I've actually seen the chip. I know it exists. I've actually seen it. So how many people in the team today?
Before I get to that, Guy, you said that you saw the platform at Embedded World. How big was it?
It's too small to see.
Well, luckily, I have the latest one, which is even smaller. It's that really tiny piece of silicon
So
right there.
that's
That
a real life demonstration of it. Actually, I mean, it is. I mean, I said at the start of this interview when I walked up to the booth and I saw it, you could reference any of my team, anybody who I spoke. In fact, you can actually reference anybody I spoke to at the show. I said, you've got to see that. You've got to go and see the Innatera. You've got to see what they've done. It's mind blowing. So yeah, it is. You a very good point. Have you actually seen it? Well, yeah, maybe with my glasses on, I have.
it's really small. And back in the day, we used to take this to trade shows, and we had a really big suitcase in which we used to carry the original demo kits. And now it's really shrunk down, and it's essentially in this small 2 millimeter by 3 millimeter chip, and that's the complete system, and it's a neuromorphic processor all in one. We've now grown to about close to 70 people. We're spread out across Europe, and actually we have people even outside of Europe working on building these next generation chips as we go towards production. We've come a very long way from the initial 7 people that we were when we first got funded.
Yeah. So this platform, ipXchange, is all about disruptive technology. Mainstream technology is incredibly important. It's the core of what makes things happen. And then companies like you come along and you disrupt it. So what our platform, what our community design engineers, obviously, big question for me to ask you is when will they be able to get when are you realistically going to be in a position to produce this in volume numbers so that they can realistically think about, is this something right for me?
We were at CES just a few weeks ago, and there we were already showing to customers and partners some of the really cool applications that we've implemented on top of this latest version chip. Incidentally, while we were at CES, we also announced that the chips are now available to early customers to sample, to really try applications out ahead of us going into volume production by the end of the year.
Right.
So that's basically what I expect by the start of next year. We will be in production. We will be able to ramp up. At the moment, we're working together with a number of customers, really trying to identify before we go into production, are there any changes which are still necessary? Is there something by way of a spec that somebody would like to tweak? We still have the ability to take some of these things in, and we're working with a lot of our early customers just to drive these requirements down.
Right. Are you able to share with me and us now sort of the some of the areas where you've got those early adopters, where you've absolutely had sweet spots? Are you able to share that now with us?
Absolutely. So we've consistently focused on a number of markets since we started, and what's important for a company like us, think of it as a big company that is still small. You have to be able to focus on markets that allow you to validate the product and the approach very quickly. And the number one within that space remains the consumer IoT, smart devices sort of verticals in devices, portable devices, whether they are security cameras, doorbells, hearable devices like earphones, portable speakers, smart TVs. These are all, applications where there has been tremendous interest coming in from OEMs and ODMs. We've partnered with a number of different sensor vendors with whom we very actively collaborate in coupling, one of their sensors together with our chips, basically to have these end-to-end application solutions that OEMs are readily able to adopt.
Yeah.
And we see this sort of traction happening a lot in the consumer space. We also see a lot of interest and traction in the automotive space, where the use cases enabled by AI have really mushroomed in the last few years. We see the willingness to adopt these even in emerging areas inside of vehicles, and understandably, automotive is a very long-term market. So it will be perhaps some time before you see these in a production vehicle. But we see a number of automotive OEMs very actively engaging and trying to make the vehicles more efficient, more a bit more safe, and possibly easier to interact with and easier to communicate with.
Okay, so now let's just break this down. Let's just break this down into the things that you said, because now we can get into the nitty gritty. Now that we understand the background and what you're doing and where you're going.
Mm-hmm.
So the thing that you said right at the start of the conversation was making sensors smart, but of course you're the bit that's smart. So typically, sensor sitting wherever it's sitting, it's sending its data into your chip. What's the if you were to take the top 5 things that your chips can be taking sensor information from, you've got your website, which we're going to talk about, but you've got things like heart monitors, sound, and that kind of thing. But what's the typical thing that the data that you've got coming into your chip? What's the typical sort of data that's coming in? What are those sensors actually doing?
Sure. So we position the chip. The chip that we recently announced was called the spiking neural processor T1.
Yeah.
The T1 is basically a microcontroller. It incorporates a RISC-V CPU alongside, our fundamental IP, which is an analog mixed signal
Yes.
neuromorphic computing engine that runs spiking neural networks, and that's the
That's
really
your clever.
ticking heart.
That's
I'm
your
sorry, say
clever.
that.
That's your
Absolutely,
clever.
yeah.
Yeah.
That's the ticking heart that makes us really so energy efficient. And we really combine those two elements and with other computing elements, provide application developers with this heterogeneous Swiss Army knife of sorts. And effectively, the chip is the first chip that the sensor talks to. It's literally the only chip that the sensor needs to talk to in order to go from raw sensor data into some sort of an actionable insight or actionable information that the rest of the system can use. Now, you can think about a very wide range of use cases. If you're talking about a wearable device that is really looking at your heart rate, we're ingesting that sort of ECG data or PPG data right at the front, and we're finding patterns within that data, and that can be timing, that can be specific patterns that occur in that data that allow you to identify a specific condition, for example, a certain arrhythmia. That is one example of classification. In the radar space, we have shown some very exciting demonstrations of presence sensing solutions to identify if there is a human standing in front of your doorbell without ever having to use the image sensor inside of the device. We've done a lot of image processing for the same sort of use cases. And within the audio realm, there's a whole range of applications going from sound recognition in a speech recognition system all the way through scene classification engines that allow the quality of music that you're listening to inside of your headphones to be continuously tuned based on the environment that you're listening to music in.
Right.
In all of these cases, we're ingesting that raw data coming in from the sensor and we're making sense of it.
Yeah. So you were with me at CS, although we didn't meet. But I must admit, I don't know how many people I met who were talking about AI. It seems that even if you didn't actually have AI in your chip, you were going to tell people and stamp the letters AI on your chip anyway. So tell me, just give me some insight as to what your definition of AI is. Because from CES, and I'm going to give you some sort of sense of what we got from CES. AI or machine learning can come in, for me, comes into two interpretations. One is a set of data sheets. You know what data you've got coming in. You know what you're looking for. You set the code to look for that data, and then you take an action off the back of that data. Some people call that AI. I'm not so sure. Second kind of AI, which is a complete opposite spectrum, which is where you're taking data and you're either going to get an answer that you don't expect, or you didn't not that you didn't expect, or you didn't expect it, or it's something that you didn't know.
Mm-hmm.
Now, where do you sit? I mean, we will put a slide in when we do this interview to show the layout of your chip. It's very clear that your clever stuff is in this this what you call analog spiking neuron synapse array. I was never going to try. I never prepare for these interviews, but there's no way I was going to come to this interview trying to remember analog spiking neuron synapse array. That was a phrase that was never going to chip off my mouth smoothly. So help us understand what you're doing, because I understand the low power bit, that speaks for itself, and I understand the speed bit. That speak not that it speaks for itself. I'm not saying that's not. I'm not throwing that away as being not very, very clever, but just help me understand the AI bit.
Sure thing.
I know you've said it's how the brain works, but explain data coming in and then what goes out.
One of the confusing bits always in trying to figure out what companies are doing inside of these different processing approaches is actually figuring out what they mean by AI. So I think that you caught onto that problem really well. And I prefer to use a whole different set of terms in describing the actual functionality that we're targeting with this chip. It's really simple. You have data coming out of a sensor, and we're interested in doing three things with that data. The first is we're interested in looking at that data and identifying patterns in it. And these patterns can be spoken words, it can be the identity of a speaker, it can be the shape of an object which is in front of the sensor or the trajectory of that object. Or we can try to identify the characteristics of the signal. So how far apart are the different beats that we're detecting from data coming out of an ECG sensor, for example. The second thing which you really care about is the quality of that data. Once the data has come in, can we say something about the signal to noise ratio? Can we clean it up in some way? Can we selectively filter that data in some way to get rid of maybe non-idealities? And how do we figure out what these non-idealities are if we had never seen these non-idealities before? That's the second thing that we're looking to do with the data. The third thing is that we're looking to adapt the system based on based on the first two characteristics that we've identified in the sensor data. So once you've identified a pattern, once you've cleaned up your signal, how do you adapt your system so that it's able to function more efficiently and more effectively? These are the three critical problems that we are looking to solve with the T1 chip. The way we do this is by deploying spiking neural networks. We do inference using spiking neural networks as well as non-spiking neural networks inside of the T1 chip. We deploy both of them in combination to do a number of things with the data. We use it to clean up the data. We use it to classify patterns in the data. We use it to do feature extraction inside of the sensor data stream. And we do all of that just to get better insight on what is the pattern content inside of the signal. Can we amplify the pattern content inside of signal and not remove some of these non-idealities? That is all the AI related part that we do using neural networks, whether it's spiking or it's non-spiking. And then we have a RISC-V CPU inside of the chip as well. And that does all of the logic part. So once your neural network has figured out what's in the data, very often you need to control some sort of system or you need to communicate to somebody else what you found. That's what the RISC-V is doing there. So really, this is the answer to having intelligence next to the sensor, simply figuring out what's inside of this data. Is it meaningful to me? Is it relevant to me? And is it going to determine how I control the rest of my system? That's what we're there to figure out.
Right. Just coming back, because I clearly understand the pattern part of it. I call it quick understand the quality side of it. Can we just more clearly define what? So signal comes in. Clearly, the first two make absolute clear sense. Then you're saying the machine will take an action. Is that predetermined or is it learning?
Well, right now, most of the applications that we do see on the market, they are the actions that you're looking to take are more or less predetermined.
They are.
You do a hand gesture in front of a system. You want the menu to move as a result of that hand gesture.
Yes.
The point here is that you could potentially train the system to detect different hand gestures. That is the changeable part. But what you want to do once the hand gesture has been detected, that is an actuation function which can be rather fixed. You don't have to learn something. You don't have to really do anything different.
So let's just use that. I mean, sorry to labour the point, but having spent a whole week at CES talking about this, it's sort of like a pet hang-up of mine, because I'm truly determined to find out what is finally the definition of AI. So let's just say signal comes in, hand gesture, right?
Mm-hmm.
It's not very clear, or no, the pattern is what we were looking for. So we understand that. In sound, let's say it's quality, so we need to get rid of some of the noise. So then we recognize that noise, we recognize that gesture, so we've seen the pattern, we've cleaned it up, so so I think that probably means we definitely know that it was what we were looking for. I think that's probably what you mean by that. Mm-hmm. What happens then at that point if it wasn't what we were expecting? What happens inside your chip at that point with that?
I think that we have to rewind this a bit.
All of this can be edited, by the way. All of this can be edited, so it's not a problem.
No, I know. I just meant, rewind in the discussion primarily because I think that the key element here is that we focus. The neural networks that we develop today are designed to find patterns in that sensor data, and they can be right or they can be wrong. They can actually detect the wrong pattern, or they can they can say that there is absolutely no pattern inside of that data.
Yes.
That is completely dependent on the accuracy of the neural network and how good the training was. Inside of a system, inside of your mobile phone, if you speak to it and the model misclassifies what you've just said, there is absolutely no way for the model to know that it got it wrong. There is no feedback loop. The model right now isn't learning anything inside of the device, the way we do things in most of the applications.
Right.
So in this particular radar gesture recognition application, I'll tell you where the AI bit comes in. I think that whenever people speak of AI, we're talking about the ability of the software application to generalize beyond the cases that it has been trained to recognize. So for example, I'm now going to move my hand in front of the screen to make this gesture. And I may train my classifier based on my hand, but not everybody has a hand that is the size of mine. People have bigger hands, smaller hands. Some people wear 5 or 6 rings on their hands, and then you have people like me who don't have any rings on this hand. And essentially, when all of these different hands are moving in front of a radar sensor, they all look different. So how do you build a neural network model which is, or how do you recognize all of these different people doing the same gesture? Some may do it fast, some may do it slow, some may get it slightly different. The key challenge is, how do you allow the software that is recognizing these gestures to be able to generalize well enough that it can recognize these gestures regardless of the size of the hand, regardless of the kind of jewelry one is wearing, regardless of the speed at which one is doing these gestures? That is the intelligence part of which it is not rule based. It is beyond that.
Yep. Is that a word that you would use? Is that a word that you'd be comfortable with using? It's adaptive. So it sees a set of rules, tries to apply a set of rules. Rules haven't necessarily been completely adhered to, but I can clean the signal. I can see that it's more or less doing what I wanted to do. Therefore, I can adapt and understand that that is either what I wanted to hear, or it wasn't what I wanted to hear, and then take an action.
I would, here in this case, I would prefer to use the word general. It is not overly specific to the constraints and the use cases or the kind of specs that we know really well. Out there in the real world, there are people that do things in ways that we couldn't possibly comprehend and characterize when we're designing the system. So the system is general enough that it can go beyond what we designed it to do and make the sort of service available beyond that initial design spec. I think that's what I'd be very comfortable in using. The reason why I'm saying not adaptive is because I think that means something else altogether. An adaptive system is one in which you can teach it to do something completely different on the field, which is one of the advantages and benefits of a neuromorphic system, is that it can learn over time. It can learn with a few data samples, it can learn out in the field, and it makes it truly adaptive. And that means that it can learn to do new things that it wasn't taught to do when it was coming off the manufacturing line in the factory.
Yes. Okay. Good. I'm glad we had that conversation, because that's another in-depth conversation. So I'd just like to move us on now, because we'll put this up on the screen as well. Wow. You've got some grand things that you say, which are amazing. So 10,000 times high performance per watt, 500 times lower energy, and 100 times shorter latency. That basically means what you're claiming is nowhere near what anybody else is doing.
That's right, plain and simple.
Just give us some background about how disruptive that is. We don't need. I think you've done a fantastic job in describing the positioning. You've done a fantastic job in describing how you got to, why you got to where you've got to. You've done a good job in then explaining to me, which I'd like to come back to just in the last question. Come back to me about what the setup is, what taking it. You've explained the system really, really well. You've explained that when our community come and look at you, they can get, or the reason why they should come and look at you. Now, just second last question. This, from everything that I saw at Embedded World, and from everything, having met you today and having listened to you talk, the reason why our platform exists is we're hunting out disruptive technology. For me, this is the most disruptive thing that we've had on our platform in the nearly 2 years that we've been doing this. So just give us some context as to how, as the CEO, as the person that's running this business, just when you're sat in your office there, what's the very definition of disruptive for you, and where do you see the future in terms of where you're going to go with this? Because potentially you're sitting on something that nobody else in the world has got. What are you going to do with that?
That's a really great question, and I'd really like to be humble at this point and say that it isn't that no one has thought about it, and it isn't that other computing technologies have not tried to go where we are going. It's just that we have such a fundamentally different approach, and we have a really good understanding of how to make compute solutions usable by people. That is really making a difference in why we're actually so successful at doing what we do. I'll give you an example of a few applications that we did that kind of highlights what kind of impact we really have. I'll give you an example of an audio application. We were doing a very simple audio classification application where you have this noisy signal coming in, and it's corrupted with noise from, the typical background noise you have inside of a restaurant, and you have people speaking. And what we were trying to do is recognize these audio patterns from this data stream. And what's very curious is that we were doing this recognition with a minuscule neural network. To give you an idea of how small it is, it has about 100 neurons or 100 activation functions, and it's interconnected by a few thousand synapses. In total, the size of that model is about 3 kilobytes or so. It's extremely tiny. It achieves an accuracy which is well in excess of 95%. What's very curious, though, is that when audio goes in, all of these different neurons and synapses activate, and the activations that we were counting inside the neural network actually are within a few hundred or a few thousand activations. And each of those activations consumes way below a picojoule of energy. So when you kind of total all of that up, you're getting 95, 96, 97% accuracy at the detection with an incredibly tiny model, which
Yeah.
is barely active and it's barely even running. It's sitting off most of the time. And you're doing all of this with a millisecond scale latency. So fundamentally, it means that you have all of the sensor data coming out in the world, and you're continuously today streaming it up into the cloud. You don't have to do that anymore. You make sense of most of that data. You extract insights out of most of that data right at the edge, and you only send the insights through the rest of the system. And I think that that is tremendously powerful because sensors in the future will not require very expensive processors. They will have this really tiny bit of intelligence integrated right next to them, able to take the data coming out of the sensor directly in the analog domain, able to extract that information, extract meaningful, and hand it off to the rest of the system to do whatever you want it to do. So sensors will not be components that spit out just meaningless data that you have to go and interpret. They now will speak actionable, functional information that you can do something with. And I think that is really the critical value and impact that we're going to be able to create on the world. What's the net effect of all of this? I think, we have three ambitions, three really big ambitions. The first is that you have a really big problem with energy usage in the world today, and we're not even measuring how much energy we spend on doing compute. I mean, do you even really think about every time you go onto ChatGPT and you type a query, do you really think about how much energy you're using? Or when you do a voice search, do you imagine that you're sending your audio up into the cloud? You don't. But there is a cost to all of this, and we see ourselves as being very critical to addressing that energy problem with all of the data that's being produced. The second challenge that we aim to overcome is increasingly sensors are going into these human machine interface sort of applications, and we see them as being very key towards the accessibility of electronic devices for the future. Electronic devices really have to, blend into your life seamlessly. They have to be at your service. You shouldn't have to explicitly command them to do things for you. They should improve your quality of life by being there in the background, in the ambience. And that's what we're there to do. We're there to add intelligence into sensors so that they can perceive you better, they can perceive your intent better, and that they can make these devices serve you better. And it's just going to lead to a more accessible digital world for all. And the final part is that increasingly we see automation and autonomy coming into all spheres of life around us, and especially in vehicles where they can have the biggest impact in terms of road safety. I think having intelligent sensors is going to be critical to how automated vehicles operate in the future. And even there, being able to do that efficiently in a way that is forward integrated in the sensor is one of our ambitions, actually
Yeah.
contributing to a safer world.
And that's all to do with the speed of the processing and getting the cleanliness of the signal, and then getting out what's really relevant to where it's got to go in order for the overall machine to work.
Yes, there are the three main things that we have to tick off in terms of requirements is number one, power efficiency. The second one is speed and accuracy of the detection. And the third one is the ease of integration and deploying software onto the solution. So these are essentially the three pillars which have been central to how we've developed the spiking neural processor as well.
Yeah, and I'm glad you said spiking neural sensor and your analog spike. I'm going to read it off the screen again because again, you're the only person I've come on through an interview, and I've actually gone. I need to prepare for this because I'm not going to remember the analog neurals synapse array spiking neural processor. There was no way that was going to rattle off my tongue nearly as easily as it. I can tell you that for a start. So, I think that brings us to a really lovely close to our chat. I think an absolutely, you know, I am the furthest away from a PhD in electronics than you'll probably ever meet in terms of doing this kind of interview. I do, of course, have 30 years of experience wandering around looking at stuff, and I just innately knew when I walked onto your booth at Embedded World just under a year ago, you were onto something that nobody else was onto, and I think you've backed that up incredibly articulately. You've given a wonderful introduction to your approach, and we look forward to hearing a lot more from you and where you take this chip and how you develop it and turn it into more real world applications. And it's been an absolute pleasure chatting to you. Thank you.
Oh, the pleasure's been all mine. I think that you have a tremendously good insight into how the entire market for AI and edge devices is shaping up. I really enjoyed our chat today, and I'd love to be able to take you on this journey together with us in showing you how neuromorphic processors are going
Yeah.
to be in practically every device that you use
Yeah.
all around you.
So are you going to go to Embedded World yourself?
Yes, I will be there with the rest of our team. We'll have a number of exciting demos on show, just like we had at CES.
So that was Guy's ipXperience with Innatera, and I had a ball listening to this back. So interesting, especially to see how many AI companies are utilizing analog technology to get that power consumption down. I think we're due for an analog resurgence within this field, and AI seems to be the thing that's bringing it home. So head to the ipXchange website and read more about Innatera's technology and apply to evaluate it today. Keep designing.